So we have seen the heat exchanger problem for parallel flow. Now we will see the same problem for counterflow. So in order to do that, we have to change the boundary conditions and we have to change the hot inlet and the cold inlet location. So go to workbench, open a new fluent and drag this geometry here. You can also drag the mesh here and go to mesh, double click the meshing, close this fluent, and then go to mesh. So this is the mesh and this is the boundaries we have defined. The thing is that here you have the hot inlet and here you have the cold inlet. So the hot inlet for counterflow problem, this will be the hot inlet and this will be the cold outlet. So change it from hot inlet to rename cold outlet and change it from cold outlet to cold inlet. So we changed the location of the inlets to make the counterflow. So first, in the previous problem, this phase was the hot inlet and this phase was the cold inlet, but we keep this phase as hot inlet and we change this phase as cold outlet, and we did the same thing at the opposite side. So our mesh is done, so we don't have any problem right now. Now go to setup and we will set up our case. The boundary conditions and all other parameters will be same. So general, we have pressure based solver, steady state problem with absolute velocity formulation. In the model section we have energy equation, and in the viscosity option we have K epsilon model, standard K epsilon model. Select OK. For material we have liquid water, and for solid we have copper. So select this copper, close. In the cell zone condition, for inlet fluid we have liquid water, select this, OK. For outer fluid we also have liquid water, select this, OK. For solid pipe we have copper tube, select and OK. Now in the boundary condition, for cold inlet, this would be your mass flow inlet, and the mass flow is 0.001 kilogram per second, and the direction is normal to the boundary, and we have the intensity of 10% and hydraulic diameter is 0.01 meter, and the temperature is 300 Kelvin. But in the hot inlet we also have mass flow inlet, and the mass flow rate is 0.001 kilogram per second, and the direction is normal to the boundary, and the intensity is 10%, and the hydraulic diameter is 0.01 meter. Select OK. Now the cold outlet is outflow and the hot outlet is also outflow. We forgot to give the temperature in the hot inlet, so go here and in the thermal section change it from 300 to 360. Select OK, and we have to create the mesh interface. So interface 1 would be interface 1 and 2, create, and interface 2, that would be interface 3 and 4, create. So we have created the interface. Now solution method we will do simple. In the turbulence dissipation rate we will do second order upwind. Also for the turbulent kinetic energy, go to solution initialization, hybrid initialization, initialize. Okay, the solution initialization has been done. So go to run calculation and calculate a little bit. So we are done with our simulation. As you can see, the solution is converged because we set up our convergence criteria at 10 to the power minus 3. So the solution has been done. So we will see the temperature contour and the plot. So go to contour, setup. We have to create the center plane just like before. So go to new surface, isosurface and mesh. Select X coordinate and compute. So you can see, so here you can see the range of the X coordinate mesh. So the ISO value of 0 will create a center plane. So name it center plane, create, close it, select the center plane, select the temperature and display. Select the field option, and here you can see, so here this is the hot inlet. As you can see, this is higher temperature, and as this goes through the outlet, you can see the temperature of the hot water is going down, and here you have this cold water is reducing the temperature of the hot water, and at the hot inlet the cold water temperature is increasing. So we will try to see the plots. So go to plot, XY plot. We have to create the line as we did in the previous parallel flow problem. So go to line, and first line would be the center line. So x0, y0, z0, x10, y10 and z1 700. This would be line 1, create, and the second line would be 7.5 millimeter apart from the center, 7.5. This would be line 2, create. So now if you want to see the line, go to graphics and animation, go to mesh, setup, display, and it will show you the whole mesh. So uncheck all of these interface, inlet and outlet, all of this, and just select the center plane, display. So this is the center plane. As you can see the mesh, select the outline so that you can see only the outline. Now select the line 1. So here is the line 1, the center line, and line 2 is the center line of the cold fluid zone. So close this, go to plot, XY plot and select the temperature. Select line 1, plot. You can see there is a single line. We will change the direction vector from X to Z, plot. Now you can see the temperature distribution. So this is the temperature distribution of the hot fluid zone. Select line 2, plot. Now you can see the temperature distribution of the cold fluid zone. So the white line is indicating the hot fluid zone. The temperature is reducing from 360 to 320, and the red line is indicating the temperature distribution of the cold fluid zone, that is increasing from 300 to 335 or something. So if you see here in the problem statement, you can see for counterflow your temperature distribution would be like this. So we got exactly like this. So this is how you can model the heat exchanger problem for both parallel flow and counterflow problem. You can also calculate the heat transfer and the overall heat transfer coefficient, and from here this temperature distribution of hot fluid and cold fluid, that the difference, you can easily calculate the log mean temperature difference, that is LMTD, and you can also calculate the NTU for your heat exchanger problem. In the next tutorial we will see some combustion problem and some multi-phase flow problem. Thank you.